Good morning or afternoon, whenever you're watching this video. This is our first video for our new unit. We are going to be jumping to Unit 10, which is circles, and going through the various sections about circles. So our first topic is Section 1. It is called Using Properties of Tangents. Another big part of this section is learning a lot of new vocabulary regarding circles. So let's jump right into it. I am going to highlight the definition. So if you are taking notes, if you were able to print the note packet, or you're just writing in your notebook, feel free to pause this video as you write things down. So the very first definition is, what is a circle? And so a circle is the set of all points in a plane that are equidistant from a given point, which is the center. So if you think about having a circle, if you have a point that is in the middle, each point, if you were to be able to draw an equal distance and connect them all, you would end up creating what's considered a circle. So every single point that lies on that black circle that I just drew is called the circle. All right, next item is the radius. So a lot of these beginning words are probably review. The radius is a segment whose endpoints are the center of the circle and any point on the circle. So these black dots that I just drew a second ago right here, these are all considered a radius, or radii in terms of plural. There's an infinite number of radii in a circle because you could just continue to draw those distances. A chord. So that is probably a new term for you. A chord is a segment whose endpoints are on a circle. So an example of a chord, let me kind of zoom in here. If I were to draw a circle and then I were to draw a segment, that is a chord. So it is a segment where the endpoints are on the circle. So you could draw multiple different chords. Now the next definition is diameter. It is a special kind of chord. So a diameter is a chord that contains the center of the circle. So if you are drawing, like if they'll say the center is right here, oops, let's say, I don't know why that won't do that. The center is right there, and I were to draw a segment through it, I have drawn a diameter, but the diameter is also a chord. Okay, a secant. A secant, see how many colors I can get in here as I highlight. I don't think I've done that one. Oh, I thought that was a different color. Oh well. A secant is a line that intersects a circle in 2 points. So instead of drawing a segment with endpoints on the circle, the secant goes right through it. So that line is a secant. So the difference between a chord and a secant, one is a segment and one is a line. Okay, finally, the word tangent. What else do we have here? Let's do a custom color. How about this crazy pink color? All right, a tangent is a line in the plane of a circle that intersects the circle at exactly 1 point, and that 1 point is called the point of tangency. So let me try to draw this while you're writing that definition down, or you are kind of pausing and listening. Let's take this color. So if I were to draw a line, and I want the line on the outside of the circle to only touch the circle right there, it might look something, oops, I missed it. It might look something like this. Okay, so a tangent is a line, first of all. All right, so if you're wanting to kind of emphasize words, it is a line in a plane of a circle that intersects the circle at exactly 1 point. So the key elements are the tangent is a line. Sometimes tangents can be segments, but we generally refer to them as lines. intersects at one point, and then that particular point is called the point of tangency. So this section is mostly about tangents. We will come back to talk more about chords and secants. Of course, radius and diameter you are hopefully familiar with from earlier math classes. So if you need to pause this video, please do. Otherwise, I am going to continue on so the video isn't too long. Okay, example 1. We are going to identify special segments and lines. We're going to practice our vocabulary. So let's tell whether the line, ray, or segment is best described as a radius, a chord, is it a diameter, is it a secant, or is it a tangent for circle P? All right, so RT. So RT is right here. So RT is a segment with endpoints on the circle. So it is a chord, but there's a better description for than chord. It goes through the center. So I'm going to describe RT as a diameter. Okay, so RT is a diameter. All right, W. Now notice it says ray WT. So I'm actually going to get rid of this. Oops, I thought I had the eraser on. I'm going to get rid of that. So let's do ray WT. So that means it's from here and it's going this way. Okay, so ray WT. Now, this is not a line, but I want you to notice that it is only touching the circle at one point. Okay, and that one point is this point T right here. So this is best described as a tangent. Okay, all right. Next one, we have segment PT, so from here to here. So segment PT from the center out to the edge of the circle, that is a radius. Radius. And finally, RQ. Let me get rid of that. So line, notice it says line RQ. So I'm going to highlight this whole item right here. So it's going through the circle, intersecting at 2 points, and that is our secant. So the biggest challenge of this section is getting used to some of these new terms. Oops. Okay, moving right along. All right, next example. And as I do these examples, feel free to pause these and try them on your own. This whole new online learning is something that is new to everyone. So maybe try to do some things on your own first and then check and see what you have down. Okay, we are going to use this diagram to find the length, find the given lengths. So I want to find the diameter of circle P. So that is the notation for a circle. And then P is the center of the circle. So circle Q in letter B, I'm looking for the circle with the center of Q, that type of thing. So diameter of circle P. All right, so here's circle P right here. So diameter is the distance all the way across my circle. So I could highlight that if I wanted to. And so if I notice, look at your scale, it says 1 grid is 4 units, so 2 grids would be 8 units. So the diameter would be 8 units. I'm just going to put U to abbreviate unit. Diameter of Q. I'm going to use my pen instead of my highlighter because it's a little skinnier. Okay, so Q. So if circle Q is right here, the diameter is going to go all the way across the circle from edge to edge. So again, each grid is 4 units. So I'm going 1, 2, 3, 4 grids. So that means I am at 16 units. Okay, I want the radius of circle P. So a couple of things, you could use the diagram, but if I have already found that the diameter of circle P is 8 and the radius is half of that, well, then I can just say that I have 4 units. And then for part D, what is the radius of circle Q? Well, the diameter a second ago was 16, so the radius is going to be half of that amount. So I would have 8 units. Okay, let's keep going. Okay, let's talk about common tangents. And you might want to add in here a definition, and I will go ahead and write it out as well. So a common tangent is, now it can be a ray or a line or a segment, but it's tangent to two coplanar circles. So I'm going to put up here, I'm going to add in here tangent to two coplanar circles. So it is one, I'm going to put the number 1 in front of this. It's one tangent, line, ray, or segment, but it has to be tangent to two different circles, and the two circles have to lie in the same plane. All right, so what I'm trying to identify here next is how many common tangents do the circles have? And I'm going to draw them too to help me identify them. So how many lines, rays, or segments can I draw where that one particular line, ray, or segment touches both circles? Okay, so for this first one, I can see if I can try to hit the top of both circles, and my tangent might be something kind of like that. Okay, and if you want to draw a line, you can by put arrows on it. So I can draw one there. I could do the same thing along the bottom. So I could, like, my second one could be like right there. But that's as many as I can do, because if I try to do one over here, I've only touched one circle. Same thing here, I would only touch one. I also can't go like this because I've gone through the circles and I've really drawn secants for both of them. Okay, so this would only have 2. So I want you to try the next couple, maybe pause this, try B and C, and see what you can come up with first. Okay, for part B, there are 4. Okay, you can do across the top and bottom, again, kind of like that. And then the other 2 are going to come through here kind of in that direction. Let's see if I can get it to work. I can go 4 like that, okay? That way it touches at one particular point. There is only 1 here on this last example, and it's right here because this particular dot is along both of your circles. So there's only 1 that is going to work on that. Alrighty. We really just have, well, we have 2 theorems. Our first theorem, though, talks about a tangent. So in order for a line to be considered tangent, of course, we defined earlier, let me come back here. We defined that a tangent touches a circle at only one point, okay? So in order to determine if a line is truly tangent, does it truly touch in one point, the following criteria apply. So in a plane, a line is tangent to a circle if and only if the line is perpendicular to a radius at its endpoint on the circle. Okay, and so what that's saying here is that the only way that this blue line right here is tangent is if it is perpendicular to the radius. Okay, because I could like envision your line being ever so slightly angled. Well, that's not a very good drawing of it. Ever so slightly angled. And maybe it touches twice. And to the naked eye, we wouldn't be able to tell. Okay, but if it makes a perpendicular right angle here, that's the only way I know it's tangent. Okay, so we're going to take a look at how do I calculate that, or how do I figure that out? So let's look at an example. So let's verify if segment AB, so if segment AB is a radius, so we are being told that this is definitely a radius, okay, of circle A, we want to show that segment BC is tangent. All right, so again, remember tangents can be segments or rays as well, but I'm trying to show that this is actually a tangent line, okay? So what I'm trying to do is I'm going to go like this, and I'm going to put a big question mark out there. All right, so how can I determine if that's a right angle? And so when you look at that picture a little bit closer, I really want to know, how can I verify that that's a right triangle? And so if you think about right triangles, what should come to mind when you see these three side lengths is Pythagorean theorem. So I'm trying to determine, do those three numbers, do 8, 15, and 17 fit into the Pythagorean theorem? Okay, so I'm going to make a couple notes here. I need to show that AB is perpendicular to BC, and I'm going to say here, use Pythagorean theorem. Actually, what you're really using is Pythagorean converse. Okay, so let's do that. So remember that your biggest number is your C. So I'm looking to see, does A squared plus B squared truly equal C squared? Okay, so let's plug it in. Does 8 squared plus 15 squared, question mark, does it equal 17 squared? Well, when you run through this, you're doing 64 plus 225, based on our perfect challenge. 17 squared is what, 289? So 64 and 225 would be, I would have a, oops, not 8, let me undo that. I would have a 5 and 4 is 9, 8, 289, yes, is equals 289. All right, so triangle ABD is a right triangle. Therefore, sorry, my handwriting is not very good with this stylus. BC is tangent. Okay, now I could have also used this triangle, this 6, 8, 10 triangle. You would have found the same answer. Okay, so what you need to, the big thing about tangents are the fact that we want them to be perpendicular to the radius. All right. Lastly, this is a theorem, but it's more property, that if you have tangent segments from a common external point, they are congruent. All right. So what that means is, if I have, if I know, let me kind of highlight here. If I know I already have tangent segments, okay, so I already know that these two are tangent, okay, and they come together at a common point outside the triangle, then what I also know is that this segment is congruent to this segment. So therefore, I can set them equal to each other and solve problems. All right, so I've got one more problem here. I'd like to apply that theorem. So you are told here that segment QR is tangent to circle C at R, and segment QS is also tangent to the circle. All right, so I'm told I have one tangent segment and I have another. I can see here that they both have a common exterior point. So my theorem says, well, if that's true, then I know that these two segments are congruent. So therefore, I can write myself an equation and set them equal to each other. So I can say that 32 is equal to 3x plus 5. So when I solve it, we can go from there. So take away 5 from both sides. So 27 is equal to 3x, and then divide both sides. We get 9 equals x, and that's all I need to find there. Okay, well, that's all for today. If you have any questions or need anything from me,